Before we proceed further, let me show you a quick demonstration about how you can visualize the results of nonlinear dynamic analysis after the analysis. So, this is you can say very interesting piece of demonstration because you will not know how actually you have to perform all this until you will cover most of the contents of this course, but at least this demonstration you can have some idea or some feel of what results I am talking about when I say that nonlinear analysis can give you real performance of your building. So, this is a program called Perform 3D. It is a product from CSI, the same company which have a product ETABS and SAP. This program Perform 3D specialized for nonlinear analysis, nonlinear modeling and then nonlinear analysis. So, nonlinear analysis have two types, static analysis and dynamic analysis. So, let us have a quick view of how if you run a nonlinear analysis once, how you can visualize its results, how interesting they are, right. So, let me open an example model. Currently, I know that you will not be able to follow several of the things in this environment, modeling environment, but just focus on some sample results, right. So, let me open this example building which is there already with this program. So, please do not worry about the options and where I am clicking, you will not be able to follow currently, but I will show you some interesting things in this. So, this is a 3-story building, it is a steel building, an example model which already is available when you install this program. So, it is run already and the results are directly available for any visualization and any you can say you can extract these results also and understand some of the things. So, this is a steel building and it is a nonlinear model, which means that it has all the inputs and capabilities which are required to simulate the yielding and all other inelastic phenomena. So, if a particular beam in this model experience a moment more than the yield capacity of that beam, the program will tell, right. It will not follow F is equal to k u forever. It has that feature in this model that it will tell the actual damage. If a connection experience some forces which are more than its capacities, the program will tell, right. So, the capacities are already incorporated in this model. Similarly, for columns, it is a steel frame building. So, columns, beams and beam column connections, these three elements are modeled as nonlinear elements, right. So, let me directly go to results and show you something. So, we have already constructed it. You can imagine that this is a model which you have to actually prepare as part of the nonlinear analysis or as part of the PBD process, right. So, let us assume and let us understand that we already have this model with us. So, let me go to analysis now and let me first directly show you the deformed shapes. So, for example, we have a nonlinear dynamic analysis already run in this. So, let me go to that nonlinear analysis results, maybe this one. So, on right hand side on this canvas we can see the undeformed shape of our building right now, right. All the elements are shown with black color, but if I want after the analysis I can color code them based on the deformation demand to capacity ratios, just like I explained in the last session, right. So, for example, the DC ratio of 1 means that the demand has already exceeded the capacity, but that capacity is not one number now, it is a capacity corresponding to each performance level, right. So, I have given a capacity corresponding to IO and then LS and then CP, right. So after the analysis, I can see which element have crossed IO level, which have crossed LS level, and which have crossed CP level. So currently I understand that you may not be able to follow this whole thing, but if I want to see which elements have crossed the immediate occupancy level in this model under this particular ground motion which I have just applied, right. So what I can do after the analysis, that I can select the immediate occupancy which I have created myself, because the program does not follow this terminology. So I have to tell during the modeling to the program that this much strain is corresponding to immediate occupancy, this much strain in concrete or steel is LS, and this much is CP. Similarly, for this is for materials, but for beam elements, for example, I have to tell that this much rotation, because the beam primarily acts in bending, and the bending deformation at member level is rotation, right. So this much rotation is IO, this much is LS, and this much is CP. I have myself input this already while modeling. Similarly for columns, right. So all the components, similarly for connections also, all the components are non-linear in it. So all the components have the capacities with them, right. Program apply the earthquake, and this is the earthquake, this is, you can say, a load case which I have just selected, and the program has run that already. Now I am visualizing the results. So what program I have done is that it takes the maximum strain produced in all the elements, or maximum rotations produced in all the beams and columns, and it divide it with the capacity of IO, LS, and CP, and based on that ratio, DC ratio, it can color code elements. So we can set a query in the program that show me all those elements which have this much strain level, or which are crossed IO level already, or for example. So this criteria I myself will select, that the immediate occupancy level is the performance level which I want to see after the analysis. I have myself defined this level, right. So this terminology I have given it myself, so therefore it is appearing in that list. I could have called it as minor cracking, moderate cracking, or severe cracking in case of concrete. I could have called it some other name also, but currently in this example structure the terminology is exactly following the ASC 41 terminology. So the standard words are used here. So I set this criteria that whichever element during this particular load case, which is a dynamic analysis load case, have a DC ratio more than 1, color code that element with the red color, and which have 0.9 to 1, color code it with orange color, then 0.8 to 0.9 is green, similarly 0.7 to 0.8 is blue, and less than 0.7 is black, right. So the elements will be classified based on that. So now let me select that earthquake load case, and what I can see here is the displacement, the roof displacement of the structure while this earthquake was being applied, right. So this is the response displacement graph on the bottom right. Now I can plot it, and the program will now color code the elements at each instant of the analysis. So currently my yellow line is here, which means the earthquake have not started yet, and I can play this animation. This is the speed for that animation. So let me speed it up a bit, maybe this one, and play this animation. So now the earthquake is you can say being applied, although it is already applied and it is just the results, right. So the program is showing the displacement in real time. At the same time, it is color coding the elements which are crossing IO level and which are about to cross, which are far more safe. So based on DC ratio, it is color coding. So the blue color beams, red color beams have already crossed IO level at a certain instant during this earthquake, right. So you can stop this animation, play it backwards, you can change its speed, right. So now IO level, you yourself know what you have set that IO level, right. So which means that these results you can directly relate with the structural damage. For example, in the steel stress strain curve which you have given input in this model, Let us say IO level is set as some percentage, for example 50% of the yield value, right. So, you can observe here that many of the beams, the steel in those beams is beyond that 50% level. Let us say LS level, you yourself set it as equal to epsilon y of steel bars, and if a certain beam cross that LS level, which means that beam is yielded already, right. Similarly, if it was concrete, you could have talked in terms of cracking, yielding, crushing, because there is concrete and there is steel also in that, right. So, there can be several of the performance levels which you can set, right. IO, LS and CP are generic terms, but you can specifically tell the program that if in the steel rebars, if the strain exceeds this number, call it this title, and that title you can see in the results later, right. For example, call it yielding in steel bars, and then at the end you can simply click on yielding in rebars, it will color code the elements, right. Actually, this data is plotted, it is actually plotting the state of each element, the damage of each element for each time instant, right. So, you can get this data extracted from the program after the analysis and exactly see that for how much time a particular DC ratio increased from 1, and then base your decision making based on that. So, there are ideas like if for a very small instant, if the DC ratio goes beyond 1 and then comes back, you can maybe tolerate that, right. So, in PBD it is not that if a DC ratio exceeds 1, it is gone. You will see the structure as a whole. For example, if there are 500 beams in a high rise building, how many are exceeding, for example, IO at a certain level. It is not that there one beam exceed a particular performance level and then you will change design, right. So, those are actually practical issues which you are referring to. So, but the information required for that decision making is there already, right. Program will not interfere in your design related issues, it will just report the performance, whether it is acceptable or acceptable within a particular tolerable limit, it is your decision later, right. For beams, beam is a local element. Its purpose is to just transfer the area load to the columns and other supporting elements. Column is a critical element, right. So, if a column is yielding, for example, in flexure under an earthquake level in which it is not supposed to yield, then obviously it requires a design decision making. Actually, in performance based design, you use the expected material properties, right. So, instead of reducing or accounting for a particular factor of safety, you try to be as accurate as possible. So, therefore, unlike the code based design where you reduce the capacities, in performance based design you increase the nominal material strengths. For example, if a concrete is designated as 30 megapascal, there will be a factor which you will apply on that 30 number to convert that nominal strength into expected strength, right. So, expected strength may be 35, 40. Similarly, for Fy, if 60 KSI is the yield strength which is used by the designer, code based designer, in PBD you may use 70 or 75, there will be a factor associated with that, and there are different performance based guidelines which give us these factors. So, the purpose of this whole exercise is not to actually design or keep the capacity ratio below 1, the purpose is the real performance evaluation, right. So, we want to simulate the damage of the building in its current design. We want to see how this design is going to perform under a certain level, right. So, no factor of safety, no load factor, So, load is not increased by a factor, load is applied in its real condition. So, all those code factors are not applicable here. So, similarly I can see, for example, life safety. Again I can plot that displacement, and this time let us focus on, for example, connections, right. So, connections are shown here by this black dot, and now the earthquake results are being shown in time domain. So, till now no damage, no element have gone in the life safety performance level. One is in the green color, one beam is in the green color, one now is in blue color. So, I can, for example, increase its speed or just drag that cursor also. So, most of the structure is, in fact all of the structure is below life safety level at this earthquake level analysis, right. So, there is a load case which I have selected at the start, right. If I change that load case, let me apply another earthquake now. So, you can see the graph is changed, and let us select, for example, CP level now, all collapse prevention, and then there are some other performance levels also, for example, life safety perimeter girders. So, this if I select, it will only check that the perimeter girders have crossed life safety or not, right. This I have made myself while doing that modeling thing, right. So, whatever I want to check after the analysis, I have to tell the program in the modeling phase, and then program run the earthquake, and then at the end produce all those results for us. So, let me select all collapse prevention. All collapse prevention, I can check back that what does it mean. So, it means actually that all the elements are selected in this group. So, any element when if it cross CP level, show me with the red color, right. So, I can plot that. So, now any red color will mean that the element have crossed CP level, right, and obviously that earthquake should be MCE level earthquake if I want, if I am checking CP, right. So, let me play that again. So, no color coding yet. So, no element have even reached to even 70% of the CP level. So, no strain even up to the 70% of the strain set for CP level. But for example, let me change this ranges, the DC ratio ranges. Let me call those elements which are like from 0 to 0.1 DC ratio, let me call them with blue color, then maybe from 1 to 3 and then 5, right, and then maybe 0.6, let me call it 0.6. So, you can see here now some blue color because I have reduced the ranges, right. So, there are few beams and few connections also, the dots with blue color, which are in this range from 0 to 0.1. Some even go beyond 0.6 also, which is red color in this case, right. So, sometimes you can for example, if I am visualizing the yielding of steel, I can give this number more than 1 also. I can say that this orange is my 1 and red is my 1.3 for example, right. So, in that case orange will mean yielding and red will mean significant yielding, right. So, all the orange will mean actually just yielded, right, and all the red will mean that they have significantly yielded, right. So, we actually know what are these levels and what are the numbers associated with that. Similarly, let me show you some other set of results, maybe modal analysis. You are already familiar with that in structural dynamics. So, you can visualize the mode shapes, you can also animate them. So, the first mode, for example, in this case is the fundamental translational mode in y direction of the building, and then if I go for the second mode, it will be the translational mode in the x direction of the building. The third will be, I think, a rotational or torsional mode, Yes, this one. So modal analysis is elastic analysis. Obviously, it will not be related to any nonlinear results. Similarly, let me show you maybe the energy plot. So this plot actually shows that with time on x-axis during that particular earthquake which I have selected, how the structure dissipated the energy of that earthquake, right. So on y-axis is the dissipated energy, and different types of energies are shown with different colors. So red color mean is the dissipated inelastic energy. It is the energy dissipated by the structure because of its damage, because of yielding, because of going into nonlinear range, right. So the presence of red color simply means that there is damage in your structure, and that damage actually starts from some 9th second, for example. If the total earthquake is 15 second, after 9th second the major damage started, right. So you can qualitatively get an idea where the energy is going, actually the energy of the earthquake, right. So in first 9 seconds very minor damage, you can confirm that in the displaced shape graph which I just showed you, right. So very useful results which you can get. Now this visualization which I just showed you, this even your client can also understand. If you tell him that red color means minor cracking, and you can visualize that specific result and show that, right. So this is something which you were not able to get with the linear elastic analysis. Here the program itself is telling you what damage your structure is going to have during a particular level of earthquake. So you run the analysis for many earthquakes, SLE, DBE and MCE, and your structure should behave in an acceptable manner under all 3 levels, then the performance is satisfactory. Another result which is actually the nonlinear static analysis results, which are also called pushover analysis. In this analysis actually we push our building in lateral direction using a pattern of lateral loads. So each story is applied with a lateral force, and they constitute a pattern which is applied actually, but that pattern doesn't have a fixed value, fixed magnitude. It starts with a very low amplitude and keeps on increasing while maintaining that pattern. The amplitude of the forces keep on increasing, and with more and more force the structure keeps on deforming in one particular direction, and at the end we plot a curve between those forces, the sum of those forces, and any deformation measure, which is generally the roof displacement. So the roof displacement is taken on x-axis, and the y-axis have the sum of all those applied forces, right. So this is kind of a force deformation behavior of your whole structure, right. Your whole structure is going to behave in that particular manner. Obviously this graph is going to be a straight line if your model is linear. The more force you apply, the more deformation you get, more roof displacement, for example. But the real structure, nonlinear structure, will not follow that straight line forever. It will deviate from the straight line after a certain level of applied loading. So this kind of an analysis give us this curve which is called pushover curve, and all the inherent limitations and discrepancies in structural design can be visualized by this exercise. For example, we can see that what will happen to our structure at what level of loading, because we are not applying a fixed loading in static lateral direction, we are applying a monotonically increasing loading. So loading starts from a very low number and it increases up till the structure is collapsed completely. So the whole, you can say, whole life of your structure, the whole spectrum of the performances is already with you, because you are keep on pushing it. So you now know that what level of displacement is expected from what level of force, and the damage also at each point in the analysis. So let me also animate those results. So currently what I am doing is that I am applying a lateral load pattern in this direction of the building, which is called H1 direction in this perform 3D modeling environment. So I am applying lateral forces at each story level in the X direction or H1 direction, and I start with a very low number and I keep on increasing it, and I visualize how the damage is progressing, how which element is the first one to go, right. So I can play that animation. So first see the whole animation. So you can see that the yellow color marker is moving, which means I am pushing it more and more, and the building is deforming in the X direction more and more, right. But and I can increase its speed also, so you can visualize quickly. So you can see that the building is completely in the X direction is swaying because of those forces, right. Now let's color code the elements also based on their DC ratios at each step of the pushover analysis, just like we did it for each second of the earthquake previously, right, or each time instant of the earthquake. So let me again bring that yellow cursor at the origin. So building is now undeformed shape, and let me color code based on the limit states or based on the performance levels. So let me click on this thing and let me select first of all immediate occupancy, and the same color coding, maybe 0.5 should be with the blue color, 0.8 should be with the green, and then 0.9, and let's select 1 here. So 1 means immediate occupancy crossed, right, already crossed. So let me now plot it. Speed should be slightly reduced, and now let's play that animation. So I am pushing it, some elements become yellow, then red, some connections cross the IO level, more and more elements are crossing the IO level as the force is increasing, and towards the end almost the whole structure have crossed the IO level, right. So this exercise alone is very useful, pushing your structure up till its complete collapse. It will tell us the progression of structural damage, how the structural damage is actually started and from where it actually moved. Mostly it starts at the base level, then more and more elements in the top stories they join that damage, right. So currently we are talking in terms of IOLS and CP, but if it was a concrete structure, we could have make maybe 10-12 limit states. For example, concrete cracking in tension, concrete cracking in compression, steel yielding in tension, steel yielding in compression. We could have make 8 or 10 major limit states, and then we see at which step of pushover analysis what actually happened, right. Which element is the first one to crack, which element is the last one to yield, right, which element is the first one to yield. So you can check the progression. Now we can use this exercise to calculate the seismic demands of approximately also, right. And the idea is that if we know the roof displacement which the future earthquake will produce, we can push our structure up till that displacement, and the forces and displacement and all the results, all the damages at up till that point are our actually the seismic demands, right. So the idea is that the point on the x axis, which is the roof displacement, we can estimate, if we can estimate that before the earthquake, for future earthquake, if we can estimate somehow the peak roof displacement which the future earthquake is going to produce, so we can push our building up till that displacement. So without performing nonlinear dynamic analysis, we can approximately obtain the forces and displacement which the earthquake is going to produce, right. So the first generation of performance based design was based on that idea, pushover analysis, when the nonlinear dynamic analysis was not that common. So what people used to do is to estimate the peak inelastic displacement of the roof which is expected to produce to be produced by the future earthquake. Let's say we get a number, let's say 10 centimeters for one particular building. So now all we have to do is push our building up till the roof displacement becomes 10 centimeter and stop the analysis there. let us say it is here somewhere, up till the yellow marker 10 centimeter, and whatever is the results at that particular time instant, analysis step actually we extract all those results and they represent our seismic demands, right. So, we can say that if now this visual which you can see now, if the roof displacement is 10 centimeter, this is the damage your future earthquake is going to produce, right. So, we approximately get the seismic demands without actually applying the earthquake, without actually performing the nonlinear dynamic analysis. There are separate methods for that. This is a big question actually in pushover analysis, how to calculate the target displacement. Target displacement means that this is the roof displacement value which the future earthquake is going to produce in your structure. So, if you can get that number from some other you can say analysis procedure or other methodology approximately, you can push your building up till that displacement and all those results are now your seismic results, right. So, there are several methods to calculate that target displacement. I think currently we should not go into the details of those methods, but let me give you few names. Displacement coefficient method, please check that in different guidelines which I will introduce next by the way, and then capacity spectrum method, FEMA 440 equivalent linearization methods. So, there are different ideas how we can estimate the most likely peak in elastic displacement if the hazard level is given, right. So, if you are given with the hazard level, this much level of an earthquake can come, based on the building properties you can estimate the peak likely displacement. Obviously, it will be the function of the hazard level. So, the hazard level will be given, the building information will be given, and those methods will approximately give you a number which the peak displacement which is going to be produced, most likely peak displacement. I will share one document in which I will show you how I myself show the results of a nonlinear dynamic analysis or static analysis. So, these numbers can give us a qualitative idea about the damage. For example, red color means that this element have crossed IO already, this is understandable. For yellow color, the DC ratio is let us say 0.9, we can call it this element is actually about to cross, and for less than 0.5 we can say it is safe, far below the IO level. So, we can qualitatively make for example our own range. For example, we could call them as damage classification as low, moderate, severe, complete, right. So, severe means 0.9 for example, or 0.8 to 0.9. Complete means gone already, red color, right. So, this give us a qualitative idea also about where the actual strain or where actual deformation lies in relative to our given capacities, right. As I have said earlier, that program will directly report analysis results. Any decision making which is related to structural design or change in design, you are the one which are you will perform that actually. Whenever we perform any nonlinear analysis, or for example pushover analysis or nonlinear dynamic analysis, we first apply the gravity load, and then that gravity load serves as a predecessor for the earthquake load. So, for example, when I perform this particular earthquake analysis, I have already applied the gravity load first, and then I applied at the end of that gravity load I start applying the earthquake. So, you can see by the way here that this is the load case number 8, which is equal to load case number 1 plus this El Centro earthquake, and load case number 1 is actually the gravity load, right. So which means that when I run this load case number 8, first the gravity load is applied, and at the end of gravity load the earthquake actually start, right. So one feature of nonlinear analysis is that we can make different load cases predecessor of other load cases. So we can take the damaged structure at the end of one analysis and start applying the next load from that onwards, right. All those degrees of freedom which have the lumped mass, they have the tendency to produce dynamic effects. But the degrees of freedom associated with dynamic analysis are generally less than those which are required to capture the K matrix of the structure. This requires some explanation. Let me try one more time. For example, we generally lump the building mass at each story level. So the program can make the M matrix based on those lumped masses. Now the lumped mass at each story level is just one mass containing, let's say, 3 degrees of freedom, right. But at the same story level there are thousands of other degrees of freedom also which are contributing to the K matrix of the structure, right. So if we perform static analysis like gravity load analysis, that detailed K matrix will be used, right, and no inertial effects of any loading or masses will be accounted. But when we perform dynamic analysis, then the complete governing equation of motion mu dot dot plus cu dot plus ku is equal to p of t, that equation will be solved, and in that M matrix only those degrees of freedom are considered which have lumped mass. So all the degrees of freedom will not be considered. So which means that for gravity load you should think of this load as some forces which are applied and not some masses which are applied, right. But if you want to simulate the inertial effects, dynamic effects actually, then you should think of lumped masses or the location of different masses. So therefore please do not confuse between mass and weight. The self weight of the structure is a separate thing in Perform 3D. It is a force which is externally applied force to your structure, right, and mass of the structure is something which is used in the dynamic analysis only, right. So in CSI ETABS generally you don't need to make this distinction. You just give the material density and that is converted into both mass and weight of the structure, right. Mass is used for M matrix in the mass source, and weight is used as a load in the gravity load analysis, right. But here you will find a clear distinction. You have to separately define masses and separately define gravity loads, right. Actually think of the analysis in terms of the governing equation of motion. If for example you model water in your computer model and run a static analysis, no inertial effects will be accounted, right. So both of the things should be met. Your model should have that capability to simulate inertial effects, and your analysis procedure should have that capability also, right. So even if you model water with some solid element or with some more sophisticated modeling technique and ultimately you run static analysis, no inertial effects will be accounted. Similarly, if you run dynamic analysis but your computer model doesn't have that capability, doesn't have those masses there which can produce that inertial effect, which can represent inertia of water, again no inertial effects will be accounted, right. So please think in terms of the governing equation of motion, everything will be clear that ultimately all dead load, live load or whatever load, they are going to contribute to your F vector, which is a fixed vector, right. So which means then F is equal to Ku will be solved in static analysis. So no inertial effects, no damping effects will be accounted, right. And if you are going to go for the time history analysis load case, then they can be accounted if the masses are there, right. Generally in CSI ETABS there is a lumped mass approach used at each node. So if there is a beam with 2 nodes, the program lumps half of the mass at one node, half at the other node, right. So it has two lumped masses at these two ends, and those actually contribute to the M matrix if you don't go for that lumped story approach, right. So similarly, I can also see the fluctuating shear forces in different elements, because I have already run the dynamic analysis. So all the responses are fluctuating, all the displacement, drifts, forces, bending moments, rotations in beam, strain values in materials, they are all fluctuating now. If I run a 50-second earthquake, all results are 50-second, right. So for example, I can visualize for example, select a particular element and visualize any result of that element. For example, let me go for shear force and bending moment module after the analysis. So again the same earthquake case, and let me select the single element, some perimeter girder, let us say this one, and if I want to visualize its bending moment diagram and shear force diagram for all 50 seconds or for whole duration of the earthquake, I can plot that. So this is bending moment and shear force diagrams. I can animate them just like I can animate any other response. So for the whole earthquake duration, how the bending moment is fluctuating, how the shear force is fluctuating in that particular element, you can see. Similarly, there are some other damage states also which you can visualize in the same module. Pushover, for example, I have given you a quick overview of what pushover is. So let me show you one pushover curve for this building. So you can see here that this is the graph between roof displacement or roof drift on x-axis and the total force which is applied as part of that pattern on y-axis. It is also called as base shear, because when you sum all the applied forces, it should be equal to the base reaction, right. So this on y-axis we have the applied force. So you can see that up till a certain deformation level and force level, the structure remained linear, but then it deviates from the straight line. Now you can also see some cuts in red color here. These are the limit states or performance points which I just defined in my computer model. So program is telling that what is actually happening at different points on that pushover curve. You can visualize that in that animation thing, but you can also check it here. If I click on one of this cut or marker, I can see panel zone shear deformation. Panel zone is that connection between beam and column. So it is now failing in shear. This is actually the IO level. IO level was defined this level. Similarly, right after that, if I click on the second cut, it is perimeter girder rotation IO, which means that now the perimeter girders have crossed the IO level at this particular analysis step. Here if I click on this cut, I can see here perimeter column rotation IO, which means from this point onwards the columns will start going into IO range, right. So if I make like 8 or 10 different limit states, they all will be shown with different markers on that pushover curve. So you can visualize or see actually what is happening to your structure at what drift level or what deformation level. Now for example, you calculate or estimate the peak roof displacement produced by the future earthquake from any other method which currently you don't know, but there are methods available for that. So let's say that number comes out to be somewhere here at my cursor of my mouse, somewhere here. So which means that future earthquake is going to push your building up till this level, right. So you can, if you have that curve and you have all the markers on it, all the damage levels, then you can directly tell that under future earthquake your perimeter columns are not going to go beyond IO level, because they are somewhere beyond that point, right. So this complete curve gives you the overall life of your building. What is going to happen to your building if the load exceeds a certain level if the load is exceed such that the building is going to get completely collapsed. So, at this last point you can call it as a complete collapse of the building, because the building is no more taking any further load and it is going to go down exceedingly high deformation level, right. So, this is kind of, I sometimes call this figure as the X-ray of your structure. If there is any inherent discrepancy, if there are weak zones in your structure, if there are certain weak stories, they can be, their signature can be captured in this figure, right. Currently this is a very regular steel building, it is showing a very nice you can say pushover curve, but if there is a sudden jump in that, which shows that there can be a possibility of sudden failure or brittle failure, and also after passing through the peak, it is not going suddenly down, it is going slowly, which means that the failure will be in ductile mode, it will not be a brittle failure, right. So, even if you exceed this IO level, even then you are safe, because you can rely on that additional ductility, right. You can also get an idea about what will be the peak displacement beyond which the structure will become unserviceable, right. What will be the peak level of force which when applied the structure will become unserviceable, right. So, there can be several information which you can get from this curve alone, right. But for the purpose of seismic analysis, you need to have an idea about what is the peak displacement against the certain level of earthquake, right, and then you bring that displacement here and put that in the same graph and then convert the results into seismic analysis results, right. In nonlinear computer model, you can also model nonlinear partition walls. So, if there is any cracking in partition wall, it will be captured in your model, right. So, one of the limit states or performance levels can be cracking in partition wall or significant cracking in partition wall. So, in the same pushover curve or during the earthquake, you can see which crack, which partition start cracking at what time actually, right. So, by the end of this course, you should be able to actually make a nonlinear model and run nonlinear analysis and produce these kind of results, right.